instead of calling it clusterfuck. We should have called it intern because we basically automated the job of an intern. So sorry to any interns in the audience.
Not that sorry.
Not that sorry. A little publicly sorry, but inside, not really sorry. So at a high level, what we're going to be looking at today is our attempt to use machine learning to group files together with some math, and then from those common file groups, programmatically extract Yara signatures so you could say, hey, find me shit similar to that in our environment, or in VirusTotal, or whatever you want to look at. So who we are, I'm Mike Sconzo, currently R&D at Click Security, and
David Dorsey, the same.
So just two dudes. We like a little bit of math, but not too much, and a lot of computers. So down at the bottom, there's this web address that's beautifully formatted. We have a bunch of IPython notebooks and code out there now that you can play with. These slides are awful. We're not going to post them. We're going to actually post the IPython notebook so you guys can have the code and play with this at home. And we'll be releasing kind of these two little utilities that you can just point at a directory of files and it will magically do things for you. Hopefully we'll have those up today or tomorrow. No promises. Okay. So Dorsey had to put this quote in there.
Yeah, I have some random quotes throughout just because Mike said this the other day. I liked it, and so that's why it's here. That's really all to say about it. I think it's the most brilliant thing he's ever said.
It tells you something about what you got in front of you, folks.
All right, so the basic question we asked is, can we group files just by their static features? We didn't want to run things dynamically because, well, we didn't. And then could we go one step further and can we turn these into Yara signatures so you can easily deploy it? And so we decided to try this on Mach-o files and your Windows executables. We tried 3 different clustering algorithms, DBSCAN, k-means, and MeanShift. But MeanShift didn't work out too well for us, so we're not really going to talk about it other than to say that it didn't work. So a little bit about DBSCAN. It clusters things by just grouping things that are densely close to each other. Go figure. The clusters can be any shape. We don't have to worry about the shape. Go figure. It scales very well with large amounts of samples, and as long as your clusters don't get crazy big, it works really well. Then for math guys, it's non-flat geometry and the uneven cluster size.
So one thing to note about DBSCAN, we'll just walk back and forth. We used scikit-learn's implementation. It has a really nice feature where you give it the number of samples you want per cluster, and if it doesn't meet that, it will say all of these samples are unlabeled, which kind of makes a lot of sense if you're looking at files, right? You would expect that there's probably a fair amount of files that are similar to one another, but you'll kind of have this tail of kind of 1 and 2 off files. So for all of our work, we said unless there's 3 files in a cluster, we're not interested in labeling it. Oh, okay. So k-means is another way that you can group data. Kind of the parameter you provide to k-means is you say, hey, I think I should have this many clusters in my data, this many groups. So here's the number of groups. You go forth and you tell me which things are close to one another. One of the nice things with k-means that we found out is it tends to group things that are highly, highly similar together and have the same values, which actually works pretty well with the way we structured our Yara generation. And then MeanShift, like I said, this one was really sad. We kind of have a motto, failure is always an option, so we totally exercised that option when we were playing around with MeanShift. Well, we won't bore you with that. So there's a couple other things you can do to your data, and all these have effects on how well, for some definition of well, depending on your use case, these algorithms function. So scaling it, right, it normalizes features, so that way you're not dealing with, one feature that's 0 to 1, and then another one that's 0 to 5,000, or maybe 10 to 1,000,000. And then the other thing that we used and made pretty liberal use of was this principal component analysis. And basically what that does is it tells you what features in your data set contain the most information, and it gives you a nice order. So it's a way to say, all right, instead of having 63 features, so 63-dimensional space, You can say, I want something a little bit smaller, maybe 18 dimensions or 3 dimensions or 2 dimensions. So that's for all the visualizations, we actually used PCA to go from these stupid high dimensional spaces that nobody can visualize unless they're highly inebriated, all the way down to 2 and 3 dimensions. So now we'll jump into Mach-o binaries, kind of a running joke. Randy the Macho Man Savage. All right, couple chuckles. I'll take it. They even wore the shirt. It's dedication. So when we talk about features, what it really means is various static attributes of these files. So we used Mach-o lib. It's in Python. It's a really nice Mach-o library. So we picked out a handful of features. The number of load commands, I don't know, is anybody terribly familiar with the Mach-o format? It's actually really nice. It's way better than PE. It makes sense. But so it's divided up into load commands, and these load commands are basically sections, and these sections do various things like, hey, load these libraries, or hey, this is the minimum version of OS X that I require to run. So we took the count and then also enumerated those, and we also threw into there the OS X version, information about the symbol table, information about the dynamic loader. Mach-o also has these fat binaries. Anybody familiar with the universal binary format? It runs on PowerPC and Intel. It does it because they literally ram 2 binaries into this one format. And then the computer goes, oh yeah, we're on PowerPC, I'm going to run this version. So those we actually broke apart and treated as 2 separate files. And we went through a bunch of iterations with feature choosing. We didn't do a whole lot of analysis on did we choose the best features. There's probably some better ones that we can choose, and there's probably some that we can get rid of. But you know, what we'll present today worked well enough for our purposes to kind of prove out the idea and get some interesting results. So the Mach-o file source started out with 527 files from Contagio and VirusTotal and VirusShare, and then we combed through the system directory on a couple Mac notebooks. So we should, in theory, if you think about kind of compiler and tool chains, should get some pretty natural groups, right? So if you get different virus families, hopefully, right, they'll be grouped together, and hopefully things compiled by Apple will get grouped together. Then on all those files, took 63 features. The reason we have more feature vectors than files, once again, is some of them were those kind of universal format binaries, so we pulled them apart. So now we're kind of in essence dealing with 639 files. So once again, we made liberal use because, I don't know, anybody here? 63 dimensions? No? All right.
There we go.
I don't even know how to do that.
Somebody had to.
So this is what a really sweet high-resolution picture of the raw data in 3D. So when graphing the 3 most important features of each file, this is what our file layout looked like. So these are all 639 blue dots. And this is what it looked like in 2 dimensions. Looks like a sideways E. Yeah. So I don't know. So as a person, right, you might see, hey, there's maybe this is a logical cluster, maybe this will be one. You can kind of visually begin to go, all right, so some things are similar, and then I've got these weird outliers, so let's see what the math does. So once again with DBSCAN, if there's not 3 things in a cluster, we're not really interested. We ran it against that. We got 21 clusters. So we ended up with 140 labeled samples and 499 unlabeled samples, sorry. Which seems mostly awful until you realize that no clusters, so using just these 63 features that we more or less arbitrarily selected, right? Malicious files were never mixed with clean files. So kind of interesting and really telling results. And the unlabeled samples we were really angry about first, but then we said, nah, maybe it makes sense. Maybe there's a lot of 1 and 2. So this is kind of what the clusters look like. The number on the left is just the cluster number, the label. Size is obviously how many files in that specific cluster, how many of them were malware, and then how many of them were clean. So you can kind of see, you know, a bunch of Apple ones got grouped together, and then potentially some malware families. And it turns out it actually did pretty well. So we just grabbed this information from VirusTotal on the samples, And despite some relative inconsistent naming from various antivirus, overall it felt like it did a really good job of grouping like malware, right? And it was even smart enough, if you will, to say, hey, you know, here's a variant E and it's pretty similar to this other variant. So now on top of this, we said, all right, well, maybe we can get less like things to be slightly more like one another if we do this PCA. I mean, as you kind of think about it, if you go from a really high dimensional space to a lower one, you're in essence throwing information away. So we reduced it from 63 dimensions to 18. So we kind of have these 18 features that we're using, and numbers kind of inverted, right? So we got 34 clusters, 452 labeled samples, only 187 non-labeled, and then 5 out of the 34 had this mix of both malicious and clean. So, I mean, you can iterate on this and you can say, well, there's probably some really nice middle ground if you have kind of that information on what's malicious and what's clean, or what should be grouped together and what shouldn't. But if you don't, probably still not a bad grouping. So more clusters, more files labeled, bigger cluster size. And this is what the colored results of the clusters look like. So you can kind of see groups of similarly colored things are by groups of similarly colored things in 3 dimensions projected from 63. So whatever that means. Kind of a slightly better picture so you can see more colored dots. And in 2 dimensions, because why not? And zoomed in 2 dimensions. So this one actually does a fairly decent job of visually showing, oh, okay, I get it. There's red dots by red dots and orange dots by orange dots and yellow dots by yellow dots. Or if you're colorblind, there's a lot of brown dots with some blue ones mixed in there. So, you know, once again, all right, so, you know, maybe it did okay, but we got some clean and some mixed. But overall, I mean, there's still kind of, you know, several samples in the same family mixed together. And it was kind of at this level that we noticed gross inconsistency at labeling samples from antivirus. Right? You know, one antivirus might label it one thing, and then another one, and then you'd switch, and they'd be elsewhere. So I like a really good example. Some not. Kind of interesting. So, yeah. Another Dorsey quote.
Yeah, so I was talking with Russ from Attack Research, and he said I could quote him on this, so you all bear witness I've quoted him on this.
He's now internet famous. So, kind of a higher level look at the k-means, right? You have to give it this number of clusters. And unless you really know I have this many clusters, there's several ways to say, all right, data, you tell me how many clusters you think I have. And the simple formula for that is just the square root of the number of samples divided by 2. One kind of interesting side note with all of this clustering, and you'll kind of see it as we go through, more often than not, and I'm sure hopefully when you guys try this at home, you'll get one really giant cluster and a bunch of really smaller ones. You can repeat this process on that big cluster, so you can kind of get a subclustered if it doesn't feel right. So that's kind of where the art form of all this comes into play, is maybe understanding what you hope to get out of the data or what you think the data represents, and ways to tease it out. So out of the 17, 6 both malicious and clean. Fairly decent, you know, nothing totally earth-shattering, but it's nice to at least see consistency among the various algorithms, and that's kind of why we chose to do a handful of them, was to do a little bit of a survey and say, all right, you know, is one algorithm going to be better at file clustering? Is one going to be worse? Does it make sense to use a conjunction of both of them? The k-means actually, in my opinion, gives you the prettiest graphs. So if you guys play with this at home or at work, give management the k-means graphs. It looks like you're super productive. I mean, you get really nice color bands. It's like science is happening. So once again, we wanted to try doing both, PCA and scaled and compare it. So pretty similar, 5 clusters, right? Both malicious and non-malicious. And a brief note too, the code that we will be releasing, you can just give it a command line flag and say, do this with PCA and choose this many dimensions, or take a guess at how many dimensions you think it should use. And it'll do all that for you, so you don't have to really do anything but what I like to call the Homer Simpson school of analysis, where you just push a button and then it does everything for you, right, for some definition of everything. So once again, really, really pretty colored bands. And that kind of makes sense that you would get these really nice bands across, various axes, since k-means really tends to gravitate towards grouping things with same values together. So jump into the Yara. This is the cool part. This is actually the part that probably took the vast majority of the work. And right as we were wrapping up on the Yara list, they said, hey, we've got some new stuff for Yara in the works, and it's going to support file modules. I was like, oh, great. I just wasted 2 months. Not that I'm bitter. I'm a little bitter. So it's kind of broken up into a couple different classes, so maybe people can use them. Our approach was a little bit different. There's some really nice Yara signature generators online that people have created, and they're generally focused around string analysis. We wanted to try and create one that was contextually aware of file structure, which at least we're not crazy, because the Yara guys announced very similar functionality, so at least we've got a nice point of validation. So there's kind of this base object, and it's just a Yara signature, and it actually does the rule generation. And then we've got both a Mach-o and a P one on top of it that support various things. So you can say, all right, for this file, create a signature that contains the file header, all the section names, and then the specific information about these various sections, or whatever combination you want. So we tried to make it pretty flexible, so when we did the signature generation, we could throw all 63 features at it, and something would stick and make sense. So the way we did the feature, or the way we did the signature generation, was pretty much a sledgehammer approach. There's much better ways to do this, and we can kind of get into why some of our failures happened, and where some of our successes were. But for each cluster, it basically says, give me all the variables that are exactly the same. And then for all of those that are exactly the same, we're going to put them together in one giant ANDed condition, and that's going to be our Yara signature. And for that, right, we load commands and all these other things. One of the cool things that we built in towards the end was all these variations of don't care bits. So the nice thing is you can make a stronger Yara signature by giving it bytes and then some don't cares in between, and we got an example of that. So I don't know if you guys can see that in the back very well, but this is actually what one of the Yara signatures generated from the clustering and then through this Yara signature generator looks like. So it tells you, right, what samples are supposed to be in the cluster. It'll give you the cluster label, the algorithm that it generated with, and then all the various parts that were fed into the generator. So for this one, it had a couple different symtab load commands, and you can kind of see all the various question marks in the Yara signature language are don't cares. So that was a way to say, hey, let's take more attributes, create a stronger signature with values that we don't care about or we know are flexible within the file format. A lot of them have don't cares as far as size. So the load command will be present, but the size will be slightly different between binaries, so we chose not to put that in there. And there's the condition. So it worked okay, right? There were parts that were completely mind-blowing, and we thought we were geniuses, and I thought I was a genius and the smartest man on earth. I don't know. And then there were parts that were entirely humbling, and we realized we were idiots and had no idea what we were doing. So here's a brief snapshot of some of the results. So you can see there's awesome numbers. There's actually one cluster where the Yara signature didn't fire on any sample. There's a bunch that it found, exactly the files that should have been in the sample. There's a couple more where the signatures probably weren't as restrictive as they could be, and we got a couple bleed, and that's kind of that 120% or 112%, right? 233% of the files. So basically what it's saying in the very last row is there were 3 samples in the cluster and the yard signature flagged on 7. And then we got to this one. Total failure, right? So in this one, there were 2 files in the cluster, and this signature generated triggered on 363. On the upside, we found the 2. On the downside, we found 18,000% more than we really should have. So, you know, it's not perfect, but at least we get some good results to go, all right, this is kind of cool. So how can we get better results? So we can play, you know, more with the clustering, again, go into subclustering, look at our feature selection a little bit better. We could support complex Yara signatures, right? This whole or business, or we could do and this or that or one of those and one of these. You can specify offsets in the generator itself. We just don't do any in here to say, look for this specific byte at this offset in the file. So a lot of room for improvement. So if people are interested in tinkering this, we're totally up for people helping. So I'll let Dorsey go on with PE.
So we did much similar things with the PE files. So we started with just some of the simple features, the file header, optional header, data directories, and a few, little bit from the resource section. We had 1,000 files total, 500 randomly selected from, you know, the multiple Windows operating systems under program files and the Windows directory. And then 500 ones we randomly selected from virus share as well, just because that was a good source. So much like we did with Mach-o, we're just going to view, you know, take a quick look at the data, just see how it looks. Here it is in the 3D again. It's the wonderful blue dots, the big kind of blob down there. Just did now. Well, so
I said it kind of looks like a penis.
Oh yeah.
Sorry.
And so here it is in 2D. It looks probably more like one. A bit more anatomically correct now. But so this is the great things you get when you visualize your data. So we ran DBSCAN on the raw data, minimum cluster size of 3 again. 7 clusters, 36 were labeled. Yeah, so that wasn't so good. So we didn't spend the time of delving into like, well, at least those 36 are grouped well. We just jumped straight into doing PCA. Much better. I'm still unlabeled half the samples, but we still got 418 in that were labeled. And it's not terribly surprising, at least to me, that we have so many unlabeled, since there's so many different malware families out there that I could easily see that we got 1 or 2 random together. And then, you know, all the different Windows files. I could see them kind of being off by themselves. 7 of the clusters had both malicious and non-malicious files, so that wasn't too bad out of the total of 63. Here's kind of a breakdown. So you can see we still got some decent-sized clusters that were, you know, grouped at least on the malware clean scale, you know, pretty well. You have the 58 on all of them are malware. So, you know, we were kind of enthusiastic about these results. At least I was.
I'm happy anytime you're happy.
And that makes me happy. So then we actually, you know, took a look at it, and actually it did pretty well to our surprise. Looks like multiple different versions of the malware family, and grouped it all together. I was quite impressed. Now we look at it in 3D, and so you see that big blob there. You can't really see anything. So if you zoom in on it, you can see a slightly bigger blob. But you can kind of see things grouped together. I mean, it's, you know, it's the eye color test. So 2D, actually, I think you can see it better. So if we zoom in again, now you can see the kind of the grouping together. It looks, I think it's a little bit easier to see in 2D. Then we moved on to k-means. We chose a k of 22 using that simple formula we showed earlier. Some pretty decent sized clusters. And here it is. It's the penis again. but now it's multicolored. So that has to count for something.
United colors of Benetton.
Yeah. If you zoom in on it, it doesn't look like it anymore. But you can see nice. I mean, this is again the k-means pretty graphs here. So then back to the results. This is actually using a PCA again, reducing to 20 dimensions. Didn't really change cluster sizes too much. We'll catch you at the end. Again, so PCA didn't change much. Still the penis there. And zooming in, another pretty graph. 8 clusters had malicious and non-malicious. You can see like the cluster labeled 1 there, mostly malware, but still a good amount of clean. But that bottom cluster, strong number of Windows files. So now we jump into the PE era. All we do is, all of this so far supports the file header and the optional header, mainly because I extracted the RVA of the resource section, which doesn't do much good when you're trying to get it from the file. So I'll talk about that in a little bit. Same thing as the Mach-o program. It does builds on all common features, supports don't cares, everything gets ANDed in the end. We have added one extra feature where it'll go look for the common values throughout the one field, and if it's the same, it will put that there, and if it's different, then you get the don't care. You can kind of see that here. So we have the file header and optional header. And then, so here's how we did in the PE stuff. So the first one there, my worst case, I only got 300, or a little bit over 300%, so way less than 18,000. So, so, and actually we had, I think I counted them, we had like 20% where we were 100. I mean, 20 the YAR samples, or signatures that were hit 100%. So this looks like, yay, I'm useful. But if you look down there at the end, then so we see some where we miss a lot, like cluster 4 there, or 1 out of 100. At least it's not 0. And I think where there might have been like 15 where it misses everything, which I don't really understand how it misses everything. I haven't figured that part out yet because it was built from the cluster, but the numbers don't lie.
It's a work in progress.
Yes, totally a work in progress. But so, so we had some success, and yeah, maybe not. But, the idea has merit, I hope. So definitely room for improvement. Like I said, we don't support resources, so I have to convert the RVA to a file offset, and then I can hopefully get some good clustering that way. We actually don't support offsetting from the PE header, so PE header can move around, so that can definitely throw off our signatures. We can catch more of our files, but then I would also not be surprised if this also makes us catch more files that we shouldn't catch. So we'll see. Start supporting ORs in there, not just ANDs, and just more fancier YARA stuff, especially as their new module stuff comes out. So yeah, so you can try this at home, and happy hunting. And
cool. Lots of questions. Perfect.
Do we have microphones? I know.
Mic for questions, or?
Yeah. I mean, we can say it and we can repeat it.
All right.
We have this one.
So,
Oh, there we go.
hey, so how are you guys doing, like, testing and cross-validation? Like, without that, like, aren't you just gonna overfit like a motherfucker? Like,
So that's a good point. So the only way we really know in this case that we are potentially over and underfitting is because we have pre-labeled data. I would imagine most people, the anticipated use case, I'll say, is you generally don't know what you're trying to label, which is why it's unsupervised. So it's hard to kind of overfit or underfit non-labeled data, right? But that's the output is the label, right? It's the cluster, this group, instead of a priori saying all of these things in this group are, you know, malware XYZ, and this is clean, and we're going to create a classification algorithm, right, using random forest or you know, SVM or whatever else. This is the opposite way, as you're saying, I don't really know what my data looks like, so this is a data exploratory tool to say, tell me what my data looks like. And more so, the idea with this is, can we take things from this more mathy Python realm that we work in and export them so that way, you know, people can find something, or they can, you know, if they've got a cluster, that they can take something out of the Python realm and into where they have the ability to run a YAR signature. Does that kind of make sense? But anyway, so the way we did the cross-validation was, after we got, since we had the labels, we were able to run the signature and say, did it hit on everything in the sample, right? So it was our false positive and false negative, and then true positive and true negative, right? By seeing what was in the sample and then what was in the sample, right? What was on the sample or in the cluster. So, okay.
Hi. What were the more informative features, and do you think you would be able to predict them when you were defining the features themselves?
So we did quite literally zero analysis on what the more informative features were. That's kind of one of the follow-up things that we were hoping to do, but never quite got around to. There's actually a really good paper that I know helped with the PE stuff that they went through and found kind of the 7 most useful features to cluster PE files on. So that was really nice for the PE stuff, but it was just kind of the shotgun effect for the Mach-o.
So you just let the algorithm run and...
Yep. There were a couple features that we learned from a classification talk that Dorsey did, was where the program jumps in kind of like the main offset. It varies based on how old the binary was, so that was kind of like just a really shitty feature that we figured in the domain was awful. So that kind of stuff, where we understood the file format enough to go, this is entirely useless to use, we were able to remove those, but from a, you know, here's a full analysis and this is why this is the most useful feature, nah, we just relied on the algorithm.
Just a little bit more. So we do have on our GitHub repo, you know, pimping that now, some classification notebooks where we talk about the most important features for classification part at least. And so we kind of can use some of that knowledge then for this. So that's some of the reasons why we chose like the file header and optional header, you know, and resources, because we had a little bit of prior knowledge.
You guys were talking about it was good enough until a certain size. What are we talking about? Like how yeah, size thresholds of your
For
data
the
corpus.
cluster size, you mean?
No,
or?
for your body of your size of your data that you're analyzing.
Oh,
Scale.
I gotcha.
Long day.
So some of the algorithms are recursive, and they just fall over after, I don't know, 10,000 or so, or 100,000, right? So in a lot of that's a function of how many features you pull out as well. So unfortunately, it kind of varies, and since we didn't do any actual true feature work, true feature analysis, I don't have a really good number for you, but good question. I know there was a question.
Ted still has his question.
No, Ted doesn't count.
I still love
That's why.
Hi. 2 questions actually. One is, can you filter the samples you put with your algorithm? Can you filter by features? I mean, if I want to know which of those samples are calling some libraries or doing this or doing that, can you do that, or you have to do that at the very beginning?
You'd have to do, so that would be part of the feature selection part. You could do it. We didn't do it. We just kind of did this match and grab for relatively easy and hopefully informative features to extract versus, You mean you could just as well do dynamic analysis on all these and then convert, right, all the registry keys and the various sparse data the libraries loaded and enumerate them and then feed those into the algorithm as features. And you'd probably get some really, really cool results.
Yeah. Okay.
We didn't do any of that, but totally like a really good idea.
Okay. And second question is, have you tried combining this with indicators of compromise?
No, but that's a good. I'd be curious.
Because I've been trying some stuff with these kind of things, and if you combine two sources of information, you get amazing results because there are some similarities in between you can play with.
Yeah, really good point. Okay, we've got 5 minutes, so probably a couple more questions. Oh, all right. We'll make sure you get your question.
Are you making the data sets available as well? So
Probably not. But if you need help getting Windows or Mac malware, we can point you to where we grabbed the vast majority of the samples online.
Okay, thanks.
Which results?
Just the output of
The shitty text files?
Yeah.
We can give you shitty text files.
big JSON blobs.
Oh, I see what you're saying.
Yeah, the JSON blobs.
Oh, I don't know.
I think we did for classification.
Did we?
Oh,
We'll see what we did for other ones,
Yeah,
and then
so
we'll do whatever we did before. Yeah.
Great.
Totally acceptable. No, it's this guy up front. I'm going to answer his question first. He's so mad now because everybody keeps ignoring him.
So, you're building signatures for the malicious files. Did you consider building signatures for the benign clusters?
Every cluster generates a signature.
Yeah.
Do you see a difference between the malicious clusters and the benign as far as which ones match better?
Oh.
We should go do that.
Yeah. We have homework. No, that's actually really good. And to be quite honest, I was totally against even looking at labels, and then Dorsey told me I was an idiot, and then we should look at labels, so I'll blame him for not thinking of that as well.
Yeah, I'll take the blame. Mainly, I just wanted to know how well we're doing. Clustering stuff is great, but okay, how did it do? We needed some sort of metric.
Anybody else? Oh, all right. So many questions. That's fine.
All right, Ted.
It's a pretty simple question, right? So what algorithm or like what mathematical function do you use to determine distance between two features?
It's generally Euclidean, except with, I think the default of DBSCAN uses Gaussian.
Okay, so that's what I thought, right? Because it's the easiest to do.
Yeah.
And you do get awesome results from this. Like anything that you can think of, like just Euclidean or Manhattan, awesome results, great place to start. For those like who want to take this and do something really cool with it, there are a ton of other distance algorithms, right? So like Levenstein's about to get mathematical on you.
Yeah.
Like, so isometric, graph isomorphism might actually like refine that and allow you to get that 18,000 way down.
Right.
You know this, right? Right? Yeah.
Yeah. And it might just be a case of like really shitty signature
trying.
generation too. Yeah.
Right. So throw all of them at it, see iterate on the results.
Right, exactly, yeah.
I thought I saw
Hand
maybe a
over
hand
there
over here
somewhere.
and then one over maybe disappeared. I don't know. Anybody else got more questions? If not, that's okay.
Did
you do any analysis of subclusters within, because based off of your features you could have, especially off the R signatures, you could have your R signature that will always match
we need to
everything in this other.
No, it was kind of on our to-do, and then we ran out of time.
Yeah. Okay. I mean, we literally finished the slides, I don't know, 5 hours ago.
This morning. You know how it goes.
Yeah.
You get all the data, and you're like, shit, now I gotta make slides. Sweet. If there's no more questions,
I think
then...
there's a guy over here.
No, none.
None.
And that was another thing that we thought of too was, can we leverage strings and use like Jacquard distance or something else and look at set unions to say, hey, these strings are common among all these files as well. Totally just a pure numbers approach. Yeah. Oh. Sure. So more from the problem, at least from my point of view, and I think Dorsey as well, from like a malware researcher, you've got tons of files and you generally know which one's which, but no matter how carefully you try to make sure everything's labeled, you just wind up this pile of crap. And like, well, I don't really know about it. So here, group it for me. And likewise, where you know the groups, here group it for me and see how well the grouping does, and then just generate the signatures for me so I can plug it into my incident response process or VirusTotals API or FireEye or something that supports Yara signatures to find similar things with you just being able to push a button. So some more exploratory and curiosity, if anything. I think we're out of time. And sweet. Stop now. Perfect.
Perfect.
Thank you. Such